Hello, I'm Nehad Dababo,
And I'm Stephen Litzsinger.
and our senior project is about learning from big data efficiently and cost effectively. On the agenda, we have project development, methodology, design, and our advisory tool, economic justification, and conclusion. So, for project development, our goal with this senior project was to get experience managing and analyzing big data and to use our industrial engineering methodologies to do so most efficiently. We began with questioning how much is enough data and whether we would see a diminishing return in the accuracy of the models after analyzing large quantities of data. We were determined to find the optimal size of predictive models. So, we began to dive into datasets looking for the best explanatory variables to predict a response. We did so with data from different industries, and what we found, though, is that there is no one size fits all answer to the questions we are asking. As the project develops, we shifted our focus to answering the question how to learn from big data efficiently and cost effectively.
Learning from big data can take many forms, and often new complex algorithms are developed to handle the challenges of big data. Our approach was to use multiple regression and backwards elimination variable selection to determine the important variables to predict a response. Backwards elimination is also known as a kitchen sink model because you start with all the variables in the model and remove, one by one, the variable making the smallest contribution. The hypothesis test for this is formally known as the partial f-test, and a 0.05 p-value cutoff was used. We performed this method on 9 different data sets, and some of the data sets multiple times to control different effects. The data sets ranged in size from 10,000 to 300,000 observations, and 5 to 500 variables. The data found online was often in different forms and structures, and much of the time in the analysis was spent cleaning and organizing the data. After the data was ready for analysis, we used variable selection techniques combined with progressive sampling to learn from the data. The concept of progressive sampling is that one can subsample from a larger set and get the same accuracy, or close to, as learning from the entire set as a whole. We used progressive sampling to see if we could find the important variables for a model before we analyze the entire set. We did this by randomly sampling subsamples from an entire set, and we did so with the starting subsample size of 50 and increasing it on a geometric sampling schedule, 50, 100, 200, 400, etc., taking 10 replicates each time. Once we got close to the entire data set size, we had to reduce the number of replicates in order to preserve unique subsamples. To make this process more efficient, we coded the progressive sampling in SAS, a statistical coding environment, and this allowed us to quickly run many replicates and output reports to collect the variable selection information. We used the data collected from the regression reports to analyze the variable selection trends as the subsample size was increased. The graph seen here is used to track the variable selection rates as the subsample size is increased. There are 2 trends in the graph. The first is that on the top of the chart, the lines take a concave down shape, and at the bottom of the chart, a concave up shape. This separation and eventual convergence is interesting, but upon further investigation, we did not see the same distinct trend in other data sets. The second trend is that as the subsample size is continually increased, additional variables lurk into the model, and we did see this in other data sets. The third phenomenon regarding multicollinearity was seen in various data sets as well. Multicollinearity is a phenomenon in which 2 or more explanatory variables in a multiple regression model are highly correlated. The extreme case of multicollinearity is linear dependence. The lurking variable effect and multicollinearity could be seen in the other data sets as well. The lurking variable trend was seen in at least one of the variables in half of the data sets analyzed. We analyzed manufacturing data to see what metrics and output measures best predicted value added. We analyzed hospital operations data to see what could best predict gross patient revenue. We also looked at GDP data for all countries and the relative inputs. We even looked at tax data from nonprofit companies to see what inputs could best predict total functional expenses. Through these many different analyses, we standardized our cleaning and organizing methods and became very efficient. Our analyses and experiences with learning on big data sets led us to the creation of an advisory tool for early attempts at big data analyses.
The advisory tool we have created is for anyone who is getting started with big data and would like to manage their own project instead of opening up their wallets to a big data consulting company. The goal of the guide we created is is to cut down on consulting costs by taking an active role in the project yourself. This is, of course, assuming that you have the time and resources to do so. The guide serves as a tool to anyone interested in learning from big data, who wants to do so in a cost-effective manner. The guide parallels the three-step process used by big data consulting companies, but in a slightly different order. The first step is data wrangling, and this is where you structure the raw data and put it in a form that is ready for statistical analysis. This is the longest part of the process and often takes 80% of the time. We use SAS and Excel for our project, but R can be used in place of SAS. Once the data is structured, it is ready to be analyzed. In this stage of the process, the statistical analysis will take the form of existing methods that are within the analyst's skill set. We use multiple regression, backward variable elimination, and jump in SAS. However, R can also be used. This is where the project reaches the fork in the road, and it must be decided what level of data engineering and platform development is required. These decisions will determine the major cost for the remainder of the project. Managing your own big data project is much more economically feasible than hiring a big data consulting company. The resources you have at your disposal for statistical analysis, data engineering, and platform development will determine the total cost of the project. First and foremost, the savings in managing your own big data project comes from the lack of consulting fees and middleman markups on data storage and processing fees. Big data companies often use the same services that are already available to anyone, such as Amazon Web Services EC2 and S3. Managing your own project also gives you the ability to directly control the level of data engineering performed without previous commitment and the costs associated with it. The economic justification is in the time saved from wrangling the data yourself. As mentioned before, data wrangling takes about 80% of the time, and so by doing that part yourself, you can see a direct reduction in total cost of the project. This is a direct cost reduction because the data engineering costs remain the same throughout all stages of the process. Thus, by doing as much as you can on your own and only contracting out what you can't do, you are being most cost effective with your project. Our work with multiple regression and specifically the variable selection procedures serve as a proof of concept for the advisory guide that we have created. We have shown that you can learn from big data with traditional tools. We have also learned that if you are taking on a big project yourself, you will likely push the boundaries of computing and storage capacities, as well as push the limits of your own statistical knowledge. The foundation of the economic justification comes from cleaning and structuring the data yourself, and this can be done with Excel as well as some efficiency help from R, a free open source statistical computing environment. The boundaries of big data are meant to be challenged, and as they continue to be challenged, there will be new methods and designs that further improve upon the quality, efficiency, and cost effectiveness of the big data projects. Future work on this project should focus on using more robust statistical methods and even venture into creating new statistical algorithms to handle the challenges of big data. It should also focus on integration into the cloud so that later parts of the guide can be more developed to help users save even more.